Hello, it's Project One. It's a team by Betsy Rosella
Yep.
and Michael Grossman. So, project overview. Uh, in this project, we require to find network data sets that we actually did. We went through a bunch of different data sets, and it wasn't easy actually to locate the data set. But finally we were able to find open flight data sets that contains flights of it contains routes, and it also contains information about airports, and actually it contains a bunch of other information that we didn't really use. We focused on two data sets. One data set was airports, and another data set was routes. And the dataset contains a bunch of information. It has airport ID, it has name of airport, city, country. Our focus was airport ID and location, geographical location, latitude and longitude. And so we try to. So our node would be airport itself, and our edge would be routes of planes flying from one airport to another, and our categorical variable was actually kind of north south split. So everything the north of the equator we call north, and everything south of the equator we call south. And our presumption was that northern airports would be much more connected, well connected, much more centered, comparing to southern airports where not as uh, industrial countries located, not as high income countries located, would be less centered. So what we done, we loaded data, and we used regular pandas, Python pandas, and so we read two datasets as I mentioned before. One dataset is airports that would become our nodes, and another dataset was routes that would become our edges. And we actually only use half of the dataset because dataset is too big, and we only used Western Hemisphere.
Hmm.
We done data transformation. We created a categorical variable based on latitude variable, and we also uh, used inner joint to because our data wasn't one to one. There was some hanging data that didn't belong, so we had to do cleaning to make sure that everything matches.
I'm gonna jump in for a minute. Yeah. So first we added the categorical variable for north south using the latitude, and then we created our node list from the routes data. Because the routes had the source and destination airports, so those were our two nodes that we connected with an edge. Uh, sorry. Oh, so actually, sorry. So we used the roots though also for the not just for the edges, but also for the nodes, so that we would make sure that we didn't include nodes that were not in our roots. And so, as Mike said, we did inner joins to make sure that everything matched up there.
Well, we focus on two centrality measure. We calculate the degree of centrality, and actually, surprisingly, the lowest centrality was also for northern airports. But we have to remember that our data is not 50-50 split. There are significantly more airports in northern hemisphere comparing to southern.
Yeah, so we just looked at the top five and the last five for each centrality measure. So for degrees, we had our top five with the maximum degree centrality at 405. But that was significantly more than the next few. As you see, the four after that go from 405 down to like 313. Um, but then the lowest all were just one connection. Um, then we did some summary statistics on the degree centrality, so we could see the average was 18 connections in the north and 10 in the south. And then we also plotted the distributions, so we could see the difference in the distribution between the north and the south. And the distributions look basically the same shape, but they just have a much different range. So the northern hemisphere goes from 0 to 400, with most of the values falling between 0 and 50. And the southern hemisphere only goes from 0 to 160, so less than half the range of the northern hemisphere, and the majority of the values being between 0 and 20. So then we did the same thing for the eigenvector centrality, looking at our top 5 and our bottom 5. None of them had very high values for this, though. If I remember right from the textbook, like the closer it is to 1, the higher it is. Everything was low, was under 0.2. But still, the highest ones were mostly, or all in the north. But even the lowest ones were mostly in the north too. But again, that could just be because we had so many more data points in the northern hemisphere than in the southern hemisphere. So again, we did our summary statistics. You can see the average for the north is 0.01, and the average for the south is 0.001. So like a tenth of almost, the northern mean. And same thing with the distributions again. The shape looks the same, but the range is very different. So in the north, it goes from 0 to 0.2, and in the south, it goes from 0 only to about 0.05, so about a quarter of the range. And again, with most of the values, though, falling at the low end of those ranges.
Okay. And also, in the end, we performed t-test just to test our assumption about behavior of airports and routes in northern versus southern hemisphere. And what we realized that degree centrality, just 1 second. Degree centrality, our null hypothesis was that degree centrality is the same for northern and southern hemisphere, and based on our t value and p values, it was confirmed that actually this is not the case. So we can with certainty say that northern hemisphere has significantly higher level of degree centrality and eigenvector centrality. So our assumption was actually, our intuitive assumption was actually correct.
So then we just visualized the network, even though we realized this is not really the optimal way to visualize this type of network. It probably should have been on a map, but just to see if we could see anything from the visualization. But there's just way too many nodes overlapping to really get much out of this. So then we just tried separating the hemispheres. So we have I think this one is the north in this one, and then the south in this one. But even still, it's kind of hard to really see what's going on with these graphs. And that's it.
Thank you.
Thank you.